In this video, we'll be going over the solutions to lab problems from week 8. So this lab is focused on introducing planes and using cross product and a little bit of linear transformations. Okay, but this first problem here, it's pertaining to planes. So it's asking us to find the equation of a plane that contains these 3 points. So you can see above here I have written what the equation of a plane is. It's a times x minus x naught plus b times y minus y naught plus c times z minus z naught. Okay, equals 0. So that's our equation of a plane. So what we're going to do is quickly introduce the components of our plane equation. So kind of similar to when we found the equation of a line. So with a line we needed a point, and with a plane we also need a point. With a line we needed a direction. However, with a plane we don't need a direction, but we need a normal vector. Well, I guess it's kind of a direction in a way, but our normal vector is a vector which is perpendicular to every single vector that's inside of our plane. So it would look something like this. So if you imagine our plane, it's made up with like a whole bunch of vectors in here. So just pointing in all these directions here. So we have a whole bunch of vectors, and every single vector in here is perpendicular to our normal vector here. So that's just what our normal vector is, and our normal vector, you can see from our equation, is represented here by A, B, and C. Okay, so these guys here, they make up our normal vector. So that's our ABC is actually this guy here. So we need to find that, and the way that we find it is by taking a cross product. So if we have 2 vectors in here and we want to find out which vector is perpendicular to both of them, we take the cross product of them. That's just a property of the cross product. It gives us a vector which is perpendicular to both vectors that we cross together. Okay, so with all of that said, I'm going to kind of draw a picture of what's going on in our specific problem here. Okay, so we have something that looks like this. We have a plane, and we have A, B, and C in here. Okay, so as we've done before, what we want to do is we want to try and figure out vectors from using these points. So we're going to draw in here. We want this to be our vector. I'm going to just choose to make this vector AB here and this vector AC here. So we want to find out 2 vectors in our plane. So AB, we know, I'm sure you guys are experts at this by now, but we take the entries in B and we subtract A. So we're going to end up with -2, 1, -1. So this is our AB vector. And we're also going to want AC. So we take the entries of C and we subtract A, and we end up with this guy. Okay, so those are our 2 vectors that are in our plane here. Okay, now we want to find a vector, a normal vector, which is perpendicular to both of these vectors. So as we just talked about, we're going to use the cross product. So we're going to go AC crossed with AB. Okay, and we end up with, if we do this method here, so if you do the cross product this way, it makes it really simple. All you have to do is essentially like ignore, so this is our first determinant here, our first entry. So what we're going to do is ignore the first entry in these 2 and just write the resulting entries here. Now we can think of a similar thing with our second entry. This is our second matrix here, or sorry, our second determinant here. So we ignore our second rows in the vectors that we're crossing together. So we end up with this. And same thing with our third. So now we're ignoring our third right here. This is 3. And we have something like this. Okay, and I should note that you always have to make sure that in your second one you put a negative. Okay, you just have to make sure that you put the negative outside of here when you're doing this method. So when you do the determinant of these guys and you figure that out, it ends up being -3, -3, and 3. So this is our normal vector here. We found our normal vector. Perfect. Now, all we have to do from here is we have to plug in all of our stuff into equation of a plane that we have written above. So we have it right here. Okay, so we know that this guy corresponds to our normal vector, our A, B, C. Okay, so we can just plug this in to our A, B, and C here. And we also see that we have to have a point. So remember, same as when you're doing the equation of a line, you need a point and a direction vector. In this case, though, we need a point and a normal vector. So our point, we're just going to pick a point and plug it into these entries here. So because this point is really easy, I'm going to pick B. Okay, and I'm running out of a little bit of room here, so I'm just going to actually erase this right here. I will move this because we need to know what our normal vector is here. So I'm going to write -3 times x minus x naught minus 3 times y minus y naught and plus 3 times z minus z naught equals 0. Okay, like I said, I'm going to pick this point because it's really easy. So I'm going to be putting it into this spot right here, this spot right here, and this spot right here. Okay, so the x value for this point is 1, so I'm going to say x minus 1. The y value for this one is also 1, so I'm going to say y minus, not y naught, 1, plus 3 times z minus 0 equals 0. Okay, when I multiply this out, so I'm just going to distribute these guys here, and I'm going to get -3x plus 3 minus 3y plus 1, or sorry, not 1, plus 3, and plus 3z plus 0 equals 0. So then I get -3x minus 3y plus 3z, and then if I move my 6 over to the other side, I get -6. Okay, so this is actually my equation of the plane right here. Okay, so I have something x plus something y plus something z equals a coefficient. Okay, so this is my equation of the plane. So once again, what did we do? Well, first thing that we did is we found 2 vectors that were inside of our plane using these guys that we were given. Then we found our normal vector. How do we find the normal vector? We just take the cross product of the 2 vectors that are inside of our plane, because that gives us something perpendicular to both vectors. Once I found this, I just am using the equation right here of our plane, and I'm plugging in my normal vector for the ABC, and I'm plugging in a point for x naught, y naught, and z naught. Okay, and it gives me something of this sort of form here. Okay, so this next question, we have to find the shortest distance from a point to a plane. So I'm going to start here by drawing our question out. So we have a plane here, and we can see right from here, just based on our formula in the last question, that essentially your normal vector is just going to be your coefficients that's in front of your x, y, and z components. So in this case, we have our normal vector. It equals, well, there's a 1 in front of the x, so we have a 1. There's no y, so it's 0, and there's a -1 in front of the z. So we have 1, 0, and -1. Okay, so that's our normal vector. I'm gonna draw our normal vector right here. And we also have our point. So this is our point P, and this equals 1, 2, 3. And so that's what we have so far. Okay, so we do have any point on the plane that we want because we're given the equation for a plane. So the first thing that I'm going to do is I'm going to choose a point on my plane, and I'm going to choose a point that's relatively easy. It just needs to satisfy this condition. So whatever x plus or minus whatever z has to equal to. So I'm going to choose my point to be, I'm going to call it PO because that's what we've been doing so far, and I'm going to choose it to be 2, 0, 0. And hopefully you can see why that satisfies or why that satisfies our equation of the plane, because if we have 2x plus 0y plus 0z, it does equal 2. Okay, so this guy is definitely in our plane. So I'm going to draw him right here and write PO, and I guess I can write it in 2, 0, 0. So my first step is I'm going to choose a point on the plane. Okay. My second step, I'm sure you guys are pretty used to this by now. I'm going to find POP. Okay, so I'm going to find this vector here, POP. So let's do that over here. So POP equals, and once again, I'm just subtracting, I'm taking this and I'm subtracting this guy. So I'm going to end up with -1, 2, and 3. Okay, so this is my POP here equals -1, 2, and 3. Okay. Okay, so what's my next step? Well, so what do I want to do is I want to find, so we're going to go back and use projections again. Okay, except for this time when we use projections, we're not going to be projecting down onto here. What we're going to be doing is we're going to be projecting this line here, so our POP, onto our N here. So we can get a vector like this that gives us our I'm going to call this, I'll call this W. Okay, so we want to get W because that's the shortest distance between the plane and here. So what we're actually doing is we're projecting our POP here, and we're projecting it this way onto our normal vector. Okay, and that's going to give us our vector here, our W. Okay, so I'm going to just write projection of POP onto our normal vector is equal to, yeah, that's going to give us our W here. So we're just going to go POP here, dot product with N over the length of N squared times our N vector. Okay. So this equals, so we have -1 minus 3 over 1 plus 0 plus 1. When we figure out what the dot product is here and our length here, and we're going to be multiplying it by our normal vector, and this is going to give us -2, 0, and 2. Okay, so this guy right here, this is actually our W. So this is our distance, or our vector right here from our plane to our point. So that's the shortest distance. It's perpendicular to it because our normal vector is perpendicular to all vectors in here. All we did is we projected our POP onto our normal vector. Okay, so this guy equals our, I guess that's my normal vector color, so I'm going to do W like that. So this equals our W, which is this guy right here. And next thing that we have to do, well, we're asked to find the shortest distance, so all we have to do is find the length of our w vector here, and that's just going to equal, we'll have 4 plus 0 plus 4 equals root 8. Okay, so this is our answer right here, is root 8. That's our shortest distance. Okay, so this question is asking us to find the shortest distance between two skew lines. So I'm just going to go ahead and draw the picture for these two lines first. So I'm going to draw something like this, and I'm going to label this guy line 2. And right here I'm going to draw line 1. So just a note about the drawing. It looks like they're just two intersecting lines, but if you can kind of try to visualize them in 3D, it makes it easier to see what's going on. So yeah, if you look in 3D, line 1 is actually like on top of line 2, so they're skew from each other, hence they're called skew lines. So here, this kind of makes it a bit more evident, I guess, if we do something like this. So if we just pick two random points on these lines here, P and Q, you can see that there's that distance between those two lines, right? So there's a distance of PQ, which is perpendicular to both of these lines. Okay, so our goal is to find, essentially our goal is to find PQ. Okay, so our goal is to find this line here, PQ. More specifically, we're trying to find the length of PQ. Okay, so what can we do to find this? Okay, so I'm going to show you guys kind of a different way to do this. So right here we're given our two equations of our lines. Okay, so I'm going to write P. So we know that P is on line 1, right? So what I'm going to do is I'm going to just write kind of the parametric sort of form of this. So you'll get what I mean in a second. So P, I'm going to write it as 1 plus 1a. I'm just going to choose a parameter a to represent my point P on my line 1. So I'm doing 1 plus 1a. Okay, so a is standing in for t essentially. Then what I'm going to do is I'm going to say negative 1 plus a times 1. So negative 1 plus 1a. And similarly for my last one, I'm going to do 0 plus 1a. So I'm going to say 0 plus 1a. Okay. And what I'm going to do is the same thing for Q here. So here, actually, I'll draw Q in this color. So same thing, I'm just going to write out like what it would look like X, Y, and Z in parametric sort of form. So 2 plus 3, I'm going to choose B for my Q, for my line 2, sorry. And then negative 1 plus 1B. And then 3 plus 0b. Okay, so I end up with these two equations here. Okay, so I know that PQ, so I know that PQ is perpendicular to both of these, of these lines that I was given. Okay. So I'm going to figure out what PQ is right now. So it's the same sort of thing that we've been doing all along. We're just subtracting vectors here. Okay, so this is my P here, and this is my Q here. So I'm just going to take Q, and I'm going to subtract P from it. Okay, so I'm going to get 3B minus A plus 1. I'm going to get B minus A, and I'm going to get 3 minus A. So this is what my PQ is equal to. Okay. Next thing that I'm going to do is, so I know that PQ is perpendicular to line 1, right? Hopefully you guys agree with that. So that this line right here, this PQ, is perpendicular to my line 1. And I think that should make sense. I mean, even from the picture here. So I'm just going to write that out here. So I know that PQ is perpendicular to my line 1, right? So if we recall dot product, that means that PQ dotted with D is equal to 0. Okay, and why is that? Because cos of 90 degrees, so cos of pi over 2, so when things are perpendicular, is equal to 0. Okay, so my dot product is equal to 0 when this is true. Okay, so what I'm going to do is I'm going to dot my, my PQ with my direction vector. Okay, so my direction vector, if you guys recall, it's just this guy right here. Okay, so I'm gonna dot my PQ vector with my direction vector here and set it to 0. So I'm gonna do 1 times 3b minus a plus 1. And I'm just getting it from these entries right here. That's my direction vector right here. And I'm going to do plus 1 times b minus a and plus 1 times 3 minus a. Okay. And this is going to give me 4b minus 3a plus 4. Okay, so we're going to keep this guy in mind right here. So similarly, I know that PQ is perpendicular to line 2 also. Okay, hopefully you guys agree with that. So this guy right here is perpendicular to my line 2, here. Okay, so same sort of thing. Then because of that, I know that PQ dotted with D has to equal 0, which means that they're perpendicular to each other. So same sort of thing I'm going to do here. I'm just going to dot it with my direction vector. So I have 3 times 3b minus a plus 1 plus, what's my vector here, times 1 times b minus a, and then my last component right here is just 0, so I'm not going to even write it. Okay, and this ends up equaling 10b minus 4a plus 3. Okay, so keep this guy in mind also. Okay, I'm just going to keep writing down here because I'm a little bit out of room, so just ignore this question here. Pretend it's not here. Okay, so I have these two equations right here, this guy and this guy. Okay, so because I have a system of linear equations, what can I do with them? Well, if I want to solve for what a and b equals, I can just put them into a matrix, right? So if I put these guys into a matrix, it ends up looking like this. And why is that? Well, it's just if I go 4b minus 3a equals negative 4, and 10b minus 4a equals negative 3. That's all I did, is I moved the single coefficients over to the solution side. Okay, when I do reduced row echelon form and I solve this guy, I end up getting a equals 2 and b equals 1 over 2. Okay, so now what I'm going to do is I take these solutions here, and I'm going to plug them into my original equations that I had here, my original points here. Okay, so I'm going to do that down here below. So I'm going to write, so when I do this, I figure out that P is equal to 3, 1, 2, and Q is equal to 7 over 2, negative 1 over 2, and 3. Okay, and you can verify this for yourself. You just have to plug A in, for example, right here and right here and right here, and you plug B in. So then you plug B in for right here, and right here, and then you end up with these guys here. Okay. Now let's think about what I actually wanted to have. Well, I wanted PQ originally, right? So all I have to do is subtract P from Q, and I end up getting a vector that's of this form. Okay. Now, because I want the shortest distance, I need the length of PQ. And so the length of PQ, it ends up being like this, which ends up as root 14 over 2. And so this here is my distance. Okay, so let's talk about the steps that we did in this problem, because it's kind of long. So when we're trying to find the shortest distance between two skew lines, we're given the equations of the lines. Okay, what we want to find out is if we have some arbitrary PQ here, which is based on our equations of our lines here, what's the shortest distance between them? In other words, what is the length of PQ? Okay. How did we choose P? Well, we chose P by just essentially writing out the parametric form of this line, and we chose Q by writing the parametric form of this line here. Okay, and we just chose our parameters. We just chose A for line 1, and we chose B for line 2. Okay, so next what we found is we found PQ. Okay, but we found PQ in our parametric form here. Okay, so we did that by just using our regular subtracting P from Q, and we found this guy here. So using our knowledge from the dot product, we know that two lines are perpendicular to each other when the dot product is equal to 0. Okay, so we took PQ and we dotted it with our direction vector, and we said that it will give us 0 because PQ is perpendicular to our line 1. Okay, from there we figured out what our equation would be here. We did the same thing for line 2. Then what we did is we put our equations into matrix form, and we solved for A and we solved for B. Okay, and then from there all we had to do was plug in our A's and B's where we needed them, so back into these guys. And then, well, I mean, we could have plugged it into here, but it's good to plug it into here and just check to make sure that those work. But so we plugged them into here, and then from there we found our PQ. Okay, our real PQ without our A's and our B's in there. From there we figured out our length of PQ, and that ended up being root 14 over 2. Okay, so sometimes math comes up with these really kind of cool and weird names for things, and this is one of them. So we're asked to find the volume of a parallelepiped determined by U, V, and W, given by this formula here. Okay, so a parallelepiped is essentially a 3D parallelogram thing. It's kind of a cool word though. So first thing that we're going to do is write down our formula. Something to note though is that this, you might think of determinant at first, but it's actually absolute value. Yeah, another thing about math is sometimes there needs to be more symbols in it. We're like reusing the same symbols for a lot of stuff, but anyway, so we have U dot V cross W, the absolute value of U dotted with V cross W. So first thing that we do here, well, the first thing I'm going to do is V cross W, which is, we have our V here and we have our W here, so we have 1, -2, -3, crossed with 1, 2, and 3. So I'm going to go ahead and just write out our our basis here. So we end up with, remember, if we're finding the cross product, we just, for this first guy here, we have 1, 2, and we have 3. We ignore the first one for the first one, and we go -2, 2, -3, 3. And then we do the same thing for the second one, so we ignore the second one, and so we get this. And then the same thing here for the third one. We get 1, 1, -2, and 2. Okay, so and then we take the determinant of each of these guys, so we would do 3 times -2 minus 2 times -3. So we do that for all of them, and we find out that our cross product is actually equal to this guy here. Okay, so this is the cross product of V and U. Now what we have to do is we have to do U dotted with the absolute value of U dotted with what we just found, V cross W. So we just do 1, 1, 1, that's our U, dotted with our 0, -6, and 4, which is our V cross W is this guy. And we end up with, it's the absolute value of it, so we end up with 0 minus 6 plus 4, which equals -2, and the absolute value of that is just 2. Okay, so our volume of our parallelepiped is 2. So our last question here is introducing something new. Well, it's not actually new because you've been doing it all along. So the whole idea of a linear transformation, I mean, it might seem new, but actually every single matrix is just a linear transformation. So it's doing something to transform space. So that's essentially what a matrix is. So the concept of a linear transformation is not new, but perhaps how we handle it in this case is new. So T is a linear transformation. So it acts on this guy to give us this guy. Our transformation acts on this vector to give us this vector, and now we need to figure out, okay, if it does that to those two vectors, what does it do to this vector? Okay. So our first step here is, I'll write out the steps here. One is we write, you know what, I'm going to give these guys names actually to make it easier. I'm going to call this one W, and I'm going to call this one U, and I'm going to call this one V. So first thing that we're going to do is we're going to write W as a linear combination of the other two. So I guess I'll just write of U and V. Okay. So we can write -1, -1, and 4 equals A. Remember, it's a linear combination, so we don't yet know what multiple of these vectors our W is equal to yet. So we write something like this. Okay, so we see that it's a linear combination. So that's our first step. Our second step is we write this in matrix form and solve for A and B. Okay, so second step here is we're just writing this guy in matrix form just like we're used to. We've done this many times before. And when we solve this guy, we do some steps, reduce row echelon, and we figure out that A equals 1 and B equals -2. Okay, so next thing that we're going to do is, so we're going to basically substitute in. Okay, so we have our T times W, okay, right? We're trying to find our transformation. Our T times W is what we're trying to find here, this guy right here. So our T times W is equal to 1 times our T times, which one did I name this one? I named our 1, 0, I named this V, okay, minus 2 times T times our U. Oh my gosh. Okay. So all I did here was replace in our A here and our B here that we found, and I just took the transformation of them both, or of both sides essentially. So you can see I did T here, so I did T here, and I did T here. Okay, so I just essentially wrote this thing right here, except for in transformation form, so with a transformation on it. Okay, so I'll just continue down here. So so my T, now I can replace my vectors in here if I want to. So I can write -1, -1, and 4 equals 1 times. So now we do already know, if we look up again, here I'm going to erase some of this because it's blocking the way. So if we look right here, our TV, well, we already have what TV is, right? Our TV is equal to this guy right here, right? And similarly, our TU, so our TU, yeah, our TU is equal to this guy here. So all I'm going to do is replace those vectors in because I already know what they equal. Okay, so I'm going to write 1 times my TU, which is 3, -2, 1, 0, minus 2 times my TU. My transformation, what it does to U is it makes 1, 1, 2, and -2. Okay. And I'm just going to add these guys up, and it's going to give me 1, -4, -3, and 4. So now what I can say is that my transformation on this guy, it's going to give me this over here. Okay, so hopefully that made sense. So you're going to just follow these steps if you're given this type of question. So 1, you want to write W here as a linear combination of your other 2 vectors that you're given here. Okay, so not the ones that have been, not when they have been undergone a transformation, but the ones, what they were before the transformation. So you're going to write your your W as a linear combination of this one and this one. Okay, and you have your A and B here. Next thing that you do, you're going to transform this in, I shouldn't say transform, that's kind of confusing. You're going to change this into matrix form, and you're going to solve for your A and your B value. Okay. Next, you're going to substitute in. So, I mean, really, you can have kind of an intermediate step if you want to, if it makes you feel more comfortable. You can say W equals 1 times V minus 2 times U. Okay, you can write something like this, and then you can take the transformation on both sides. So transform this side, and then the transformation on this side. Okay, you can totally do that if it makes it easier. I just skipped that step. Perhaps I shouldn't have, but I did. So that's all I was doing here. So I'm substituting my values for A and B back in, and then I'm taking the transformation of both sides here. Okay, I already know what my value for the transformation on V is. It equals this guy. I already know what my transformation on U is. It equals this guy. Okay, so all I did was plug those into here and plug this into here. And when I solve for that, it just gives me my transformation of my W vector.